Hey all, and welcome to today's session, Making Your Mobile Apps Data Available Offline. My name is Kevin Riedelsheimer, and I am a developer advocate for SAP. Today I want to talk about enabling your mobile apps to work with business-critical data from anywhere at any time, especially when being disconnected from the internet due to bad or wonky bandwidth. Before we go into detail on how we can achieve that goal, I want to introduce the SAP BTP SDK for iOS. When downloading the SDK, and this is true as well for the Android SDK, you will use three tools to create mobile apps. The mobile SDKs are our Swiss Army knife for creating beautiful and highly performant mobile apps. Next, we have the SAP BTP SDK Assistant for iOS or the Android Wizard to bootstrap app creation and generation of code necessary for security, connecting to the backend, data access, and more. And lastly, we have SAP Mobile Services on the SAP Business Technology Platform for managing and maintaining our mobile apps, users, and the tools for the support staff after the app has been deployed to the different clients. Let's talk about the SAP BTP SDK for iOS. As you can see, the SDK contains a ton of different frameworks available to you as a developer for creating innovative apps. From a great UI component library all the way to foundational APIs and open source projects for creating augmented reality experiences and integration for conversational AI. We have it all. But today we will focus on the data service frameworks, SAP OData and SAP Offline OData. One is to provide general APIs for managing incoming and outgoing OData backend calls, and the other is for providing the offline feature we want to explore together. But before we do that, let's take a look at the other tools I've been talking about. When you download the iOS SDK, you will automatically get the SAP BTP SDK Assistant for iOS, which is a native macOS app. This app provides you with a ton of features like creating SAP Mobile Services cloud configurations necessary for managing your iOS apps. It also creates Xcode projects, including so-called Swift proxy classes generated out of the metadata document of your OData service, representing the app's data model. In addition to the Swift proxy classes, you will get a complete data access layer, providing you APIs for creating, updating, and deleting data in the backend. You don't have to write your data access layer yourself. The assistant does that for you. The assistant also generates several pieces of UI if required. An example, an onboarding flow or a master detail UI flow to have a quick starting point for your own user interface. The assistant can do far more than that. It can generate code for remote notification handling or provide translations of your strings using SAP Translation Hub. As you can see, the assistant is a powerful tool speeding up the initial development time of your iOS project. And no worries, the same is available for you as an Android developer using the Android Wizard. To connect our apps to the backend and various cloud services available in SAP BTP, we're using SAP Mobile Services. SAP Mobile Services is a powerful service on BTP allowing you to manage your deployed apps, and it functions as a middleware coming with a ton of features like providing an easy way to upload client logs, managing client resources like PDFs, images, or any other binary needed within your mobile app. It also functions as a server for sending push notifications and allows for exchange of core ML models and AR scenes during runtime, allowing you to push these binaries to the mobile app without the need for shipping an update. Most importantly for us today is the OData offline synchronization feature. This feature allows us to synchronize data between the backend and the client, and it works hand in hand with the SAP Offline OData framework on the client. So you might ask yourself, why would I need to provide data from the backend to the users in an offline manner? And the answer is simple. It is not only a common practice for modern native mobile apps, but also to make business crucial data available to your users when they need them most. When network bandwidth is non-existing, like in basements, oil rigs, retail stores, hospitals, warehouses, or any other remote locations. As an example, we have been working on a project in the past where data needed to be available within a healthcare service facility in Berlin. For those of us who have been to Berlin, it is a city with a lot of old buildings out of brick and concrete. This facility couldn't provide Wi-Fi in the whole facility, but only in certain parts of the building. The availability of business crucial data was necessary everywhere in the facility, so we made sure that the data is available offline on the device. There are a lot of other use cases where data needs to be available offline at any time. So how do we get started enabling offline OData for our apps? First, we add the offline feature to the mobile app configuration in Mobile Services. Then we add the logging feature to our application and client log upload feature to our cloud configuration on Mobile Services. This is not necessary, but we highly recommend it to receive network traces and client logs while you develop your app, as well as in production. Within the app, you have to initialize the offline store, which we recommend doing during the onboarding process after the user has successfully authenticated and accepted all necessary usage agreements. The initialization of the offline store will require an initial download of the defined offline OData. Now that the offline store is initialized, you can implement CRUD operations using the generated OData access layer or by implementing your own access layer. You can now download and upload data while being connected to SAP Mobile Services. And lastly, you can customize offline synchronization behavior and performance in the SAP Mobile Services cockpit if you need that. So you might ask yourself, well, why do we do all of this work if we could just use caching? And your question is absolutely valid. The answer, as you would suspect, is it depends. So let me explain while showing you this comparison table. So if you want to store your most recent data with a fixed cache size for a short time to improve your general performance of the app, then caching is a perfect way to go. It is lightweight and it can improve the robustness of your app. If you require your app to store a larger amount of data for an almost unlimited time on the device, you need the full set of operability and you expect your app to be offline for non-trivial periods of time. It makes sense to have a data subset available in an offline store on the device. So in general, we can say that for the use cases we want to tackle, true offline synchronization is required for an optimal user experience and to ensure full availability of business relevant data and functionality. So in a real-life scenario, it would make sense to combine both of these approaches within the app. For example, storing product images in a cache for faster loading, but the product information could be loaded out of the offline OData. So now we understand the procedure of how to generally set up offline OData with SAP Mobile Services and the SAP Offline OData framework. We understand the differences between caching and the offline first approach, where we use caching to improve performance and robustness of our app by storing the most recent used data for a short time, and use the offline first approach for availability of business crucial data for non-trivial periods of time with having full operability. So now let us look at the available features with SAP Mobile Services and the mobile native SDKs. So we have full CRUD support, allowing you to operate on the data like you would expect with most backend services. We can view the usage statistics within SAP Mobile Services, allowing you to monitor network activities and handling of the offline store. We provide data security on the device as well as on SAP Mobile Services to ensure secure data handling. Currently, there is a full support of OData v2, and OData v4 is partially supported by providing the Lambda operator. Conflict detection is done using e-tags, and failed requests are handled automatically using specific heuristics and proper error logging. We also support handling of repeatable requests. And repeatable requests support prevents the client from sending the same requests over and over, reducing unnecessary work on the backend. Another great feature is the ability to share the OData offline store through SAP Mobile Services with different clients. That approach speeds up the initial download of the defined data subsets for all subsequent clients after the first client populated the database. A Progress API makes sure that you can display the download and upload processes to the user, and so improving the user experience. And users often generate hundreds or even thousands of requests on the device before uploading them. Processing them all at once can be expensive on the backend, particularly if users do this at the same time, for example, at the end of a business day. However, many requests can be merged together, which is handled by Mobile Services and the SAP Offline OData framework. There are also ways to undo changes the user made to the data, allowing for easier rollbacks. And that brings us to the underlying technology on how the SAP Offline OData framework operates on the client. SAP Mobile Service Offline OData is built on top of an in-house technology which has been designed and used in synchronizing backend data to mobile devices for the past decade. On the client, we are using an ultralight database, which is a proprietary standard designed for mobile devices and is based on SQLite. There are two databases used: the store database, which stores the data, and the request queue database, which stores the requests between client and server. The store database stores the user's view of the data, which includes many other tables such as those which contain the relationships between entities. The request queue database stores the modification requests post, put, patch, and delete made by the user. It also includes many other tables such as those which support request optimization. This whole approach to database synchronization is what makes SAP Offline OData very powerful. The technology can replay messages flowing between client and server, and so server-side auditing becomes possible in the first place. A typical end-to-end scenario looks like the following. We have our end users to the left using our app client either on iOS or Android. The client is connecting to SAP Mobile Services for data exchange, and Mobile Services functions as a middleware routing the requests from the client to one or multiple backends. These backends can be deployed within SAP BTP or on-premise. If the backend is on-premise, a Cloud Connector instance most often needs to be installed for propagating the user's credentials and allowing access to the on-premise backend. If the app gets started the first time, an initial download for the subset of initial data is required for the store database to be available. The initial data is declared based on a list of so-called defining queries. Defining queries are genuine OData queries which indicate what subset of the data on the backend to synchronize. Since they are built on top of OData, these queries are very powerful, providing features like synchronizing full datasets and allow you to use operations like filters on them. So when the client first connects to Mobile Services, the metadata document of the OData service gets requested. After that, the client is sending the defining queries to the backend through SAP Mobile Services. The OData backend is executing these queries, and Mobile Services is populating the initial store database based on the responses for these queries. The offline store name and the offline store itself get downloaded to the client. At this point, all subsequent requests made by the client get sent to the local store database. SAP Mobile Services stores the initial store database, which allows other clients to download the already initialized store. This makes the OData offline initialization process quicker, as the database is already populated and only needs to be downloaded to the client. If the client requests another download of the store database, the queries are again sent to the backend using Delta tokens in form of e-tags. Now only modified data is sent to the client instead of the full database. In the process, any client-generated entities are discarded. The server-provided entities are updated, added, or removed. And then the request queue is replayed, recreating the client-generated entities. Here you can see how such a defining query can look like. In this example, the query asks for the dataset of the table product. Because all data operations the user undertakes go against the local store database, the app must synchronize the manipulated data with the backend at some point. So you as the app developer must determine when and how users are allowed to upload and download data. This can be done automatically based on a schedule or network availability, or via the UI manually by the user. All executed requests done while being offline get written into the request queue store. Queue store, yeah. When the synchronization is being triggered then, SAP Offline OData will execute the requests in the request queue store against mobile services, which is forwarding the incoming requests to the OData backend. To allow delta synchronization, e-tags get attached in the HTTP header of these requests. Your backend should support e-tag delta checks for this to work. In case your backend is not supporting this technology because of a legacy backend or any other reason, mobile services can substitute and handle the delta synchronization for you. But it is recommended that your backend supports that. SAP is providing the mobile backend tools if you want to build an OData backend supporting e-tag delta checks. You can find the link to the tool in the description of this video. So the backend is executing the requests and sends a response to mobile services where necessary. The backend only sends the data that has changed since the original e-tag has been created. And all changes get applied to the offline store in mobile services. And after completion, sends the updated version of the offline store to the client's representation of the offline store database. We recommend using the Progress API to notify the user about the process of his operation. You can also use the remote notification service to send a push notification to the user about the status of the update. Important to know is that the Offline OData framework will run several optimization algorithms on the requests queue store to reorder and/or consolidate requests to help reduce backend processing time. What you can see in this diagram is what happens in the error case. In case of an error response from the backend, a virtual error archive entity set is populated on the client, allowing the user to ultimately see and resolve errors that occurred on the backend when processing the requests. So if the client can receive the response because of network issues, mobile services, or if enabled, the backend will store the response. If the request is received again when the client is online, the backend checks the request and resends the original response. So during the download process of the offline store from mobile services, an automatic check for changes in the metadata document has been executed. It is expected to have only additive changes to the metadata of the OData service. That will allow for seamless application of the metadata changes to the offline store. This process allows for operation replays using the request queue. In case changes are not additive, an update of the app is required because app code might need to be adapted to avoid errors. The initial download of the data can be long depending on how the data is sliced. To avoid bad user experience through synchronous execution and a resulting UI log, the download can be executed in a synchronization task. The synchronization task can be activated via the API and allows the download to continue if the app enters the background, which can highly improve the user experience. So make sure to utilize this feature if possible. So now we come to the last topic I want to talk about today: error handling and conflict resolution. So in case OData requests submitted by the Offline OData framework fail during the upload process, the errors are returned to the client and the entities involved are put into an error state. The returned errors are written into the error archive and the correlating events into the event log. The error archive is a virtual entity set in the offline store database and can be read by the client. So that being said, the client is responsible for solving these errors to remove the error state from the affected entities. The best way to resolve occurring errors is by issuing OData requests fixing those errors. Another possible solution is to flush the failed requests within the request queue database, which will trigger a merge algorithm to merge failed requests with potential new requests. This approach should be handled carefully because it can cause data loss due to flushing the failed requests. This is your last approach of handling these errors. So OData supports conflict resolution using HTTP tags. When an entity is updated, the client specifies the timestamp of the entity. If the timestamp does not match the current server version of the request, it is rejected. So offline OData apps can use e-tags to detect and prevent conflicts from happening. Rejected requests are added to the error archive, as we know, for the client to fix. So another approach would also be the last one wins approach. The backend does not detect conflicts in that approach and allows the last modification to be performed. But be aware that this approach can result in loss of data because of overriding it. So most issues occurring while uploading and delta synchronization can be prevented by optimizing the business and app process of data manipulation. So keep the following in mind to take measures against such potential issues. Determine the set of entity types whose entities will be modified and implement appropriate input validation for those to secure syntax and business rules. The SAP BTP SDK for iOS provides UI controls which have input validation built in, so make sure to utilize them. Always think about potential business logic errors outside of the app's control and minimize these. That is why you should make sure that the app development teams and the backend teams work closely together and optimally define an OData service suited for the app's needs and purpose. Always make sure the user has enough information to help solve or best case avoid concurrent conflicts. And lastly, make sure you have appropriate logging within your app to make the debugging and support process easier. Use the SDK's built-in logging framework, the network tracing, and the client log upload feature of SAP Mobile Services to maximize logging and error tracking. And with that, I want to close today's session. Providing data offline and handling data synchronization is a very powerful but complex topic, and I would need a full day to go into all detail. This session should give you a general understanding and a nice head start into your offline journey. I have linked additional resources like the official documentation and learning material in the description of this video. If you have any questions, please feel free to comment below this video or reach out in the SAP community. There we have a complete section just about application development where you can raise your questions. The community as well as us advocates can engage with you and help. So download the SDK today and try out the offline feature to get a better grasp of the topic. To build a mobile backend, check out the mobile backend tool. And with that, I wish you happy coding and I see you next time.